Here's our second polynomial inequality. Again, we have a polynomial compared to 0, and as in the last problem, it is always easiest to work with the polynomial in factored form if we can do so. This polynomial, we see we can factor out an x from each term. And then we can further factor the resulting quadratic. This one factors as x minus 3 times x minus 5. And the reason we like the factored form again is because we can easily read off the zeros for the polynomial, and it also makes testing the subintervals an easier process. Here we have zeros 0, 3, and 5, and so we put those numbers on our number line and test each of the subintervals. In the right interval, I can test the value of our polynomial at 6. Putting 6 into our polynomial, we get a positive times a positive times a positive. So our polynomial must be positive for x greater than 5. In between 3 and 5, we find the number 4. So let's test the sign of our polynomial at 4. Plugging in, we get a positive times a positive times a negative. So our polynomial is negative on that subinterval. Continuing with the other two subintervals, we can test 1, positive, negative, negative. So we're positive in that subinterval. And let's go ahead and test negative 1. Negative, negative, negative. Okay. So we know the sign of our polynomial in each of these subintervals. So now it's just a matter of writing our solution. We want to know when the polynomial is less than or equal to 0. Well, it's negative on this leftmost interval from negative infinity up to 0, and it's negative on the interval from 3 to 5. And because we are talking about less than or equal to, 0 is also a solution, because 0 makes the polynomial equal to 0. So we'll use a bracket to include the 0. 3 also makes our polynomial equal to 0, as does 5. So because of the less than or equal to sign, we use brackets at the endpoints of our subintervals. And to finish it off, we use the union sign in between.